Okay, good afternoon, everybody. So we were talking about implementing a list of integers in C. So just to quickly remind you what's going on, our list is just a plain old struct. Right? Inside that structure is a pointer to an array of int. We keep track of the number of elements in the list in size, and we need to keep track of how big our array is with the member called capacity. We have a function called listinit that makes a list that can hold up to that many elements. Right? And it returns a pointer to a list. Now, you could write this so that it returns just a plain old list instead of a pointer. And I'll show you how to do that in just a second. But we were returning a pointer to a list. So the correct way to do this is to make a list object. So I'm going to use, so t will be a pointer to a list object, and I'm going to allocate memory for that list object. Right? So I need to malloc enough memory to hold one list structure. Right? So in other words, enough memory to hold one pointer, one value of type size t, and a second value of type size t. I then need to allocate memory for the array. Right? So I'm going to use malloc to allocate that many chunks of that size. Then once I have the array, I can just set the member in the structure. So t array equals array. I can set the capacity, so t capacity equals capacity, and I can set the size to 0. Right? Now, this is returning a pointer to a list, so whatever you do, right, your pointer that you return, it must be pointing to something that's dynamically allocated. Right? So if don't do the following, right? So don't make just a plain old list structure, right, and initialize it to have this right capacity and size, right? Here again we allocate, so we correctly dynamically allocate memory for the array, right? And then we write t.array equals array. That also will compile just fine, right? And then return the address of t. So you must not do that. Even though the array is dynamically allocated. The problem here is that if you just make the structure t, right, that thing there has automatic storage allocation. So in other words, its lifetime is the lifetime of the function. Right? So as soon as this function completes, the object t no longer exists, right? Which means the pointer that you returned is no longer valid. Even though the array that's inside the object was dynamically allocated, right? The object itself is no longer there. So if you write that, now the unfortunate thing is if you write that and you test it on a very small program, it might actually work. It's not until you test it on a slightly larger program where you start to realize that there are problems, right? That your object t really doesn't exist anymore. So whatever you do, don't or never return a pointer to something that has automatic storage. Or automatic lifetime, right? The lifetime of that object is only the length of the function itself. Oh, so let me, I guess there is another way to write this. So instead of returning a pointer, you could return just a list object, and that actually would be fine. So for example, instead of writing that function, you could write the following. Let me just get rid of the stuff you're not supposed to do. Right? So you can safely return just a plain old list structure. Right? And now the way you would do that is you would actually do something like this. List t, that's fine. Okay, if you just want to return a plain old structure, this will actually work. Right? So here, instead of returning a pointer to a list, I'm just going to return a list structure object. Right? So now inside you can go ahead and do that. That's fine. Right? So go ahead and make a little structure t. Right? Dynamically allocate memory for its array. That's the important part here. Right? So I need to dynamically allocate memory for its array. Set the array belonging to the structure, and then I can return a copy of the structure. That's fine. So the way that C returns a copy of the structure is it makes a new, it basically returns a copy of this thing here. right? So in other words, it makes a copy of that object. So the capacity of the returned object is equal to the capacity of t, right? The size of the returned object is going to be 0. The pointer, its array, right, will be equal to whatever this pointer is. And that's fine, because that pointer points to something that was dynamically allocated. So this does, in fact, work. If you wanted to write your functions so that they returned list structures instead of pointers to list structures, you can, in fact, do so. But the way that I've set up this code is to return a pointer to these objects instead. Yeah?
What would the benefit of that be?
There's no real benefit or disadvantage either way in this case. The structure is so small that copying it doesn't impose any penalty, right? So when you copy one of these structures, you're literally copying a pointer, a size t object, and a size t object, right? So there's almost no cost to copying this as opposed to returning a pointer. There's no real advantage either way in this particular example, right? It's just that you try to use pointers everywhere you can when you're teaching this course so that people get used to using pointers. Okay? So what I just said holds true for everything else, for all the other functions that take in pointers or return pointers to lists, right? You can, in fact, rewrite all of these so that they take in plain old list, so that the parameters are just plain old list structures, and the return values are just plain old list structures as well. Okay, what about copying a list? So if I want to copy a list that's pointed to by, other, right, then it's basically the same thing all over again, right? I want to return a pointer to a copy of the list, so I need to make a new list object, right? So I make a new list, So I allocate memory for that list object, right? Allocate memory for its array. So its array is the same size as the other array size, right? So the other array size is just the capacity of the other array, right? Times the size of int. Right? Once I have that array, I can set the array for t to be equal to that array. And now I want to copy the contents from other ARR into TARR. Right? Now you could write a loop to do this. Right? So just write a little loop for I equals 0, I is less than other size, I++, and then copy the elements over one at a time. Because this is a fairly common operation in C, right, where you're copying chunks of memory to somewhere else, the standard library has a function that does that for you. So memcopy is the function that copies memory from one location to another location, to another non-overlapping location. Right? So the way memcopy works is you say, where do you want to copy the memory into? So I want to copy the memory into the new array. The array belonging to the new list to the new list object t. Right? Where do you want to copy it from? So I want to copy the memory from the other lists array. Right? And how much memory do you want to copy? Well, I want to copy the number of elements in the other array, right, times how big each element is. Right? And so the documentation for memcopy is in the string, the declaration for memcopy is actually in string.h. You would think it would be in standard lib.h, but it's not. It's in string.h. Right? That's the old version of the function. Right? So it takes a pointer to the destination, right? A pointer to the source, and the amount of memory to copy. Right? Where the amount of memory, again, is specified in terms of the number of bytes, right? Or multiples of char. If you're wondering why it looks like this, right? So notice that C99 changed the declaration of the function. It inserted this keyword called restrict. Right? Restrict isn't anything that we're concerned with in the course, but if you want to know what it is, it's right here. Right? So restrict can be used with a pointer declaration. So basically it says that the function promises not to access the memory pointed at by a pointer, except using that, it promises not to use a different pointer to access the memory that's pointed at. So for example here, right? Not right there. Where's restrict? Right here. Right? So you've got that pointer called pointer A, right? So if the function says that pointer A is a restricted pointer, right, then the function is saying the only way it's going to access the object pointed at by by pointer A, sorry, is using pointer A. So it's not going to make another pointer and try to get into that object. The reason you want to do, or not that you want to do this, the reason that this was added to the standard is because the compiler can generate different code if it knows that memory isn't being accessed by more than one pointer. And so that's the only reason. So your compiler can generate slightly more efficient code in some cases. Yeah, so if you ever need to copy chunks of an array, memcopy is the fastest way to do it. The standard library says that this is the fastest way to copy memory from one place to another. It even says that most compilers will, if the compiler can detect that you're writing a loop to copy stuff from one array to another, it will change that to memcopy anyway. Assuming your compiler is set up so that you have optimizations turned on. Okay, so once you've copied the array, go ahead, copy the capacity, and copy the size over, and away you go. Right? So if you're taking 124, or if you remember what you took from 124, this is really just a constructor, and it's really just a copy constructor. It's just that the way you have to write things is different in C compared to Java. Right, and then finally, don't forget to return your pointer to your list T. Okay, what about size? Size is easy. Right, I just access T size, and that's the size of the list, so that's no problem. Get is easy, right, because I have an array. So if I want to get an element at that index, right, I just need to go into the array and look at that element. So I just do that. Right, now this is an array. Oh wait, that assert is incorrect. No, that assert's not fine. Right, so it would be nice if you actually did some error checking. Right, so in other words, if you actually validated the index. So because its type is size T, right, that's unsigned, so I never have to worry about a negative index. What I do have to worry about, though, is that that index is too big. Right, so I want to make sure that the index is, in fact, less than the size of the list. Right, if you assert that and you have assertions turned on in your compiler, right, and you call get with an invalid index, your program will crash and it will stop running. And there will be an indication of where it happened. Right, so it'll say this assertion failed. Right, so at least you know that you tried to access an element of the list with an invalid index. Set is the same, right? I want to I want to change the element at that index, and I want to replace it with that. Right, so I can just go into the array, change the element in the array to that element. Right, this set also returns the element that was overwritten. So go into the array, get the old value, and then return the old value afterwards. All right, so for add, we need to possibly add capacity to the array, right? So we need to expand the size of its array. So it's useful to add a separate function that actually expands the size of the array belonging to T. Right? So add capacity is that function. So if I need to increase the capacity of T's array, then the easiest way to do it is to use realloc. Right? So remember, realloc is the function that reallocates a previously allocated chunk of memory. Right? If there's something in that chunk of memory, it will copy the contents of that memory over into the new array. Right? So I want to reallocate T's array, right? And I want to make it twice as big as it used to be. Right? So the capacity becomes 2 times the old capacity times the size of int. Assuming that works, I can just go ahead and update T now. Right? So its capacity is now larger by a factor of 2. Right? And its array is now equal to the new array. Okay, so add is where we possibly need to increase the capacity of the array list. Right? So if our array is currently full, right? So in other words, if the size of the list is equal to the capacity of its array, right? Go ahead and add capacity. Right? Add capacity fails if it can't allocate memory, sufficient memory. Right? So the way I've written add capacity is to return true if it succeeds and false otherwise. Right? So check if we could actually add capacity. If we can't, we just return false. Once you've added the capacity, go ahead and set the last element, or the last, go ahead and set the element at t size to the new element. Right? Because remember, t size is always one bigger than the last, is the one bigger than the index of the last element that's currently in the list. Don't forget to increase the size of your list by 1, right? Because you just added an element to the list. Okay, so insert is the function where we might have to move elements in the array, right? So remember, when you insert into the middle of the array, you have to move all the elements at that index and beyond 1 position to the right. And so we need to move a chunk of memory now. Right. So let's ignore this stuff for now, and let's go down to here. All right, so the first thing I need to do is I need to make room for the new element. So I need to shuffle over a bunch of elements in the list. You could write a loop, but because this is C, and it's often the case where you're moving a bunch of elements in an array around, there's a function that does that for you. Right? That function is memmove. So memmove will move memory from one location to another, and the two memory locations can be overlapping. Right? So in other words, you can move a part of an array into the same part, into another part of the same array. And the way it works is, the first thing is, that's the destination, right? So that's a pointer to where you want to move the memory to, right? That's a pointer to where you want to move the memory from, right? So I want to move the elements starting at the index where I'm inserting into the list, right? I want to move them 1 position to the right, right? So the address of that is just t-array index plus 1, like that, right? How much memory do I want to move? I want to move n elements, right? And each element is an int, so a size of int. Now, how many elements do you want to move? You want to move the number of elements in the list minus the index where you're inserting, right? So if you just do a little bit of if you just draw a picture and do a little bit of arithmetic, right, you can easily figure out that that is the correct number of elements to move, right? Instead of using address of, you can use pointer arithmetic directly, right? So I want to move all the elements in the array starting at the given index. Right? So I can get a pointer to that element just by using t-array plus index. Right? I want to move them 1 position to the right, so I just need to add 1 to the stuff that's highlighted. Right? And so that's just t-array plus index plus 1. Right? So depending on where you are in your comfort level with using pointers, right, either one works fine. Right? You can use indexing and take an array and use the address of operator, or you can use the pointer directly. Either one's fine. Once you've moved the elements over, go ahead and set the element at the, go ahead and set the index of the array to the new element. Don't forget to increase the size of your list by 1 because we just added an element. Right? Okay, so let's back up and now let's look at the special cases. So here's the case where you're trying to insert an element into the list, but the list is full. Right? So if the list is full, just go ahead and add capacity again. Right? The case here is where you are trying to insert the element at the end of the list. Right? And so here the index is equal to the size of the list. Right? If you're trying to do that, then the easiest way to do that is just to call add. Right? Add will reallocate the array if it needs to, and then add the element to the end of the list. Right? And finally, let's look at the assert statement. So this assert statement is slightly different than all the other ones that are validating an index. Right? So most of our validations, the index is always less than the size of the list. Right? For this particular method, it's allowed to be equal to the size of the list because that indicates you're adding to the end of the list. Okay, remove is similar to add, except you now shift elements to the left, right? And so again, it's easy. You just use mem move, right? So to remove an element, you shift at a given index. You move all the elements starting at the next index one position to the left, right? So my pointer to the element at the index that's one to the left of the place where of the element we're removing, right, is just the element at the index plus 1. Sorry, that's the index of the element 1 to the right. Right? I want to move that to the left. Right? So I want to move that into the array element at index. Right? How many elements do you need to remove or move? Right? So here it's the size minus the index minus 1. Right? Again, this is easy. If you draw a picture, right, you can get the correct value for n here. Right? Don't forget to decrease the size of the list by 1 because we're going to remove an element. Right? And then this version of remove actually returns the old element that was overwritten, which we got way back up here. Okay, so that's basically that. So those methods basically give you a functioning list, right? You can add, you can remove, you can insert at the end. Sorry, you can add at the end, insert into the middle, remove, and you can make a list. Right? So there are, if you want to, you can now add extra methods that make your list a little more usable. Right? If you were in Java, you would implement equals. Right? I don't think I actually do that for this example. Right? If you wanted to print a list, or if you wanted to give your users a way to print the list, you could consider adding toString, which is right here. But you're going to see very quickly it's a huge pain to implement. Right? So let's see what's required here. All right, so I want to produce a string representation of a list. So the way it's going to work is it's going to have a square brackets on both ends. It's going to have the elements of the list, and they'll be separated with a comma and a space. Right? So if the list is empty, it's not too bad. Right? So if the list is empty, I need to, also I have to return a string. Now remember, strings are just arrays of car. Right? If I'm going to return an array from a function, I have to dynamically allocate that array. Right? So if the list is empty, I want to return that string right there. Right, so I want to return square bracket, and then don't forget there's a null terminator on the end. Right, so I need to return an array of length 3, which I'm allocating right there. Right, so there's space for my array of length 3. You have to dynamically allocate it because if you don't, the pointer that you return won't be valid anymore. Right. I now need to copy the string into S. Right? So you could do this manually. You could write S0 equals square bracket, S1 equals closing square bracket, S2 equals \0, or just 0, I guess, would work. But sprintf or string copy is a lot easier here. Right? So I'm going to use sprintf, which we haven't seen before. So sprintf is like printf, right? So remember, printf prints something to the screen. sprintf prints it to a string instead. Right? So sprintf, that's the pointer to the string where you want to print into. Right? So I want to print into S. Right? That's the string. Yeah, that's correct. That's the string that I want to print into this. That's what I want to print into the string. Right? And then you can go ahead and return S here. So that's the empty. That's the case where you have an empty list. Now the case where you have a non-empty list becomes harder. Right? And so the reason it becomes harder is because you have to allocate enough memory for the list, for the string that holds the characters of the string representation of the list. Right? The complication that you run into here is that you don't know how big each string is for each element of the list. Right? You know you got a bunch of ints, and that's all that you know. right? So the situation you're in here is you either constantly reallocate the memory for the returned string, or you try to figure out what is the biggest string that might be returned by this method. Right? So that's the way I'm going to do it. I'm going to do the biggest string that might be returned by this method. All right, now how do you figure out what is the biggest string returned by this method? Right? You have to figure out what is the longest string for an int. Right? Now what problem do you have? Right? The language doesn't say how big an int is. Right? It just says that an int must be at least some number of bytes. It doesn't tell you how many. So now you have to figure out what is the longest string on your, what is the longest int on your computer. Right? So the way I'm going to do it is I'm going to make a temporary buffer of length 100. Right? That's almost certainly bigger than the longest int on your computer, right? At least for the foreseeable future. Right? 100 digits is a lot for an integer value. I'm going to print that integer value into my temporary buffer. I'm going to print the largest or the longest integer value into that buffer. The longest integer value is the most negative integer value. So that's int min in C. Right? And int min, that might be a different value that's a value that depends on your operating system and your computer architecture. Right? Okay, so how am I going to print that into temp? Well, I need to format that integer, that value, as an integer value, right? And so you can specify the formatting string here, right? So this is just like printing an integer value to the screen, except I'm going to print it to a string, right? So there's my formatting specifier. There's the value that I want to print. That's the string I want to print into. Right? Now that I've printed that value into the string, I can ask the string how long is that value. Right? So the maximum int length for my particular computer, I can get by using string length of that string. Right? Now I've got the longest int that you can generate. So now I can figure out what is the longest string that's possible for this list. Okay, so I need room for each value. I need room for the comma and the space that separates each value, right? Then I need two more, right? One for the opening square bracket, one for the closing square bracket, right? But I also need one more, right? I need one more for the null terminator, right? But I actually have an extra one here. Right? Because I'm separating the elements with a comma and a space, there's no comma and space on the last entry. Right? So I actually have two extra spaces right there. So I can just add two here, or I can actually add one and be fine. Right? But that's where those numbers are coming from. Notice that this is not very easy to do. Right? There's a lot of bookkeeping that you have to do. Now I have to print the string, each element into the string. So how's that going to work? Right? Okay. So the first thing I'm going to do is I'm going to print the first element and the opening square bracket into the string. Right? So opening square bracket, first element, right? So that's t array 0. I'm going to print that into the string using sprintf. Right? Sprintf returns the number of characters that were printed into the string. So that's n. Right? So that's the number of characters that were used to print the first element plus the opening square bracket into the string. Right? Notice I've got this pointer p that points at the start of the string s. Right? So what I'm going to do is I'm going to advance p by n. Right? So that moves the pointer so that it moves the pointer into my buffer so that it points at the next free spot in the buffer where I can print again. Right? Now I'm going to write a loop that processes the rest of the elements. Right? So I start at index 1, right? Go up to, but not including the size of the list. Right? Each time in the loop, I'm going to print a comma and a space, followed by the next element in the list. Right? And I print that into the string pointed at by p. Right? So remember, p is my pointer that moves through my buffer, and it always points at the next spot at where I want to print into the buffer. Right? every time I print, I remember how many characters were used, right? And then I advance the pointer by n locations each time. Right? Finally, at the very end, right after I've printed all the elements, I can print the closing square bracket. Right? And sprintf will include the null terminator for you. So you don't have to worry about adding that yourself. Right? Finally, you can return s. Right? And you've got your string representation of your list. Right? Your buffer is probably too big. Right? So in other words, where do I allocate the buffer? Here. Right? So s is probably a lot bigger than it needs to be, because it's probably the case that all your integers are not integer min. Right? If you wanted to, before you return the string, you could realloc it. Right? So you can realloc it to the string length itself, +1 for the null terminator. Right? And that would trim any excess capacity from the array. So could realloc here. Right? But again, notice that compared to like Java or compared to Java or Python, producing nice textual representations of your objects, not so easy. Right? There's a lot of stuff that you have to worry about. Okay, there's another version of list to string. I don't think I want to go over it. You can look at it in your own time if you like. Right? So one of the problems with the first version is you have to calculate how much space is needed in the returned string. Right? The other problem is that it's always allocating memory for a string. Right? So in other words, suppose you write a loop and you want to print the string each time in the loop. Right? So if all you have is list to string, right, then every time in the loop, you're allocating a new array or a new string. Right? Printing the string, next time through the loop, allocate a new array, print the string, and so on and so on and so forth. Right? If you're in that situation, it makes much more sense just to recycle the array that's being used to hold the string. Right? And so the way you do that is you ask the caller to pass in an array that you can write into each time. Right? And this saves you the problem of having to constantly reallocate memory. Right? Remember, every time you allocate memory, the caller has to remember to deallocate it. Right? So every time they call list to string, they have to remember they have to deallocate that memory. Otherwise, they end up with a memory leak. So it makes a lot more sense, in some cases, to let the caller provide you with the string to write into. Right? And that's the second version of list to string. Right? This one has its own problems, and I'll let you look at the implementation on your own to see how it works. Right? I'm never going to ask you to reproduce something like this. Notice how long the method is, right? The function is. Right? There's a lot of bookkeeping that you have to do in order to get this to work right. It does, in fact, work, though, which is nice. So I'm just going to run a little example program. Okay, so this is list demo. This tests out our list class our list structure that we just made. Right, so it starts out with an empty list, right? And now it starts to add stuff to the list. Right? So it adds one element, it adds a 0, and then it prints the list using list to string. Right? So you can see here it just adds a bunch of values 15 times. Right? So we end up with a list with the values 0 through 14. It then tests out remove, so it removes the first element of the list every time and prints the list. Right? So 1 through 14, 1, then 2, then 3, right, all the way down to the empty list. Right? And then it does the same thing. This time it uses the second version of the function. This time when it removes the elements, right, it uses the second version of list to string, where the caller is passing in an array to write into. Right? And the array to write into is much shorter than the actual list, string representation of the list. Right? So the array that you're writing into is actually this long. Right? And so notice that this actually does correctly print out that string representation every time. Right? So it never overruns that buffer, right? And it fills up that buffer with as much of the string, as many as the list elements as it can, right? Before it runs out of space. Right? So you can just play around with those and see how it works. and fiddle around with the list demo program if you want. All right. Okay, so moving right along. So now we want to look at implementing a stack using linked nodes. So this is similar. This is basically a very simple version of a linked list. So instead of using an array, I'm going to represent the stack using these things called nodes. Right? Everybody should know what. So everybody here knows what a stack is, right? Yes. So let me just whip through these very quickly. Don't need that, and don't need that. Okay, so nodes, right? So instead of using an array, what I'm going to do is I'm going to store the elements of our stack in this thing called a node. Now a node is an object that can store an element. So for example, it could store an int if we have a stack of int. But more generally, right, it can store a pointer to an element. Right? So instead of storing the element itself, we're going to see later on that it may be useful to store a pointer to the element instead. Right? The reason we want to store a pointer to the element, pointer to the element, is because eventually we want to make a generic stack or a generic list. Right? So in other words, a stack or a list that can hold any element type. Right? So instead of having a stack that can just hold int, it would be nice if I could write one C file and produce a stack that can hold anything, right? That would be a lot more useful. The way we're going to do that, though, is we're going to have a pointer to an element instead of storing the element directly. Right? So a node also holds a pointer to 0 or more other nodes. Right? So in a stack is just a linear collection of elements, right? So the elements are arranged one after the other, right? The first element is the top node, the second element is the second node, and so on and so on and so forth. Right? So our node for a stack is going to hold our element. For the time being, it's going to hold an element directly. And then it's going to hold a pointer to the next element in the stack, or the next node in the stack, sorry. Right? So our node for our first stack implementation is going to hold an element. And then it's going to have a pointer that points at the next node in the sequence. Right? So if our stack has one element in it, then there's one node. Right? The pointer to the next node is null, which indicates there is no next node. Right? So there's your element, there's your link. Right? Your link's just a pointer. Right? If I want to push another element on top of the stack, I need to make a new node. Right? I need to store the element in the node. And then I need to hook that node up to the old top of the stack. Right? So I need to set its link so that it points to the previous top node. Right? And then I need to adjust the top node so that it points at the new node. Right? But remember, top's just a pointer. That link is just a pointer. Right? So I can do all of this with just a little assignment. Right? And then don't forget to add 1 to the stack size because you just added an element to the stack. Right? To pop an element from the stack, right? So in other words, to remove that 3, right? I need to remember what is the element in the node, right? Because I need to return that element, right? So I need to remember there's a 3 there, like that, right? I want to move my top pointer so that it points at the next node, right? Now the next node, right? Top's a pointer to this node. That pointer is a pointer to the next node. So I can just do top next and get to the next node. Right? I want to subtract 1 from the stack size. Notice that node disappeared. I'm going to have to free the memory that was used for that node. Right? So there's something I have to do there. And then I want to return the value that was popped off the stack. Okay, so let's see how this works. So this is going to be similar to our list. So here's our stack header file, lstack header file. So lstack is linked stack. Right. Again, we have an opaque type. Right? So I'm going to declare that there's something called lstack, but I'm not going to tell you how it's implemented. Right? So I tell you lstack is just a name for a structure that's also called lstack. Right? The definition of the structure is inside the source code file. Right? So our lstack structure, right, is just a pointer to a node. Right? So it's a pointer to the top node, and it's we keep the size of the stack itself, right? The number of elements in the stack. Right? So what's a node? Well, a node is just a structure as well. Right? Each node holds an integer element, right? And it holds a pointer to the next node in the sequence. Right? The order in which you define these, oh, that's not true. That's fine. We have a type def up here, so that's fine. lstack, okay. So just like a list, we're going to have a little function called init. It returns a pointer to an lstack object. Right? We'll have an isEmpty method function that returns true if the stack is empty. Size returns the number of elements in the stack. Right? Push pushes an element onto the stack. Right? And pop pops an element from a stack. Instead of having a toString, we're going to have a function that just prints the stack. Right? That's a lot easier because I can just use printf. And then finally, with the list, we have to free the list, right? So we have to free, we need a function to free the stack. Let me go back to the list because we need a function to free a list too. Right? So if someone gives you a pointer to a list and they ask you to free the list, right, then you need to free two things, right? So remember, inside the list, there's an array which was dynamically allocated. So we have to free that array, right? So deallocate the memory for that array. And then finally, once you've deallocated the memory for the array, you can now deallocate the memory that was used for the structure itself, right? So there's two calls to free here. Okay, so inside the stack, its init function looks a lot like the list init function. Right? Allocate memory for a stack structure, right? So malloc size of stack, or size of lstack. Right? Now in an empty stack, there is no top node, right? So my top pointer can just be null, right? And the size is 0. Right? And then return s, and away you go. Okay, is a given stack empty? Well, it's empty if the size of the stack is 0, so that's easy. Right. What's the size of a stack? Well, we're keeping track of it inside of the structure itself, so that's easy too. Now what about push? Okay, so push pushes an element onto the stack. Right? So to push an element onto a stack, we make a new node because we need to store the element somewhere. Right? So make a new node. Once you have the node, copy the element into the node. Right? Now I need to connect the new node to the old top element. Right? So the old top element is stored inside the stack structure itself. Right? So n next is equal to stop. Right? And then now update stop. Right? So stop is now, or the top of the stack is now the new, now points at the new node. Right? And then don't forget to increase the size of the stack by 1. Right? And then return true in this case to indicate that we successfully pushed the element onto the stack. Okay, so what about popping the stack? So to pop the stack, you can't pop an empty stack. So we're going to assert that the stack is not empty. Right. Remember, you have to remember what is the top element of the current stack. Right. So the current top element is that. Right. Remember, top points at the current stop points at the current top node. So top elem is the current element at the top of the stack. At the end of the function, I'm going to return that element. I can now adjust the pointer to the top of the stack so it points at the next element. Right? So stop equals top next. Right? Decrease the size of the stack by 1. Right? And now in the case, so in C, you have to remember that whenever you pushed something onto the stack, you dynamically allocated a node, right there. So whenever you pop an element off the stack, you have to deallocate the memory that was allocated for the node, right? If you don't, you end up with a memory leak, right? You end up with memory that's being used for, or held onto for no purpose. So you have to free the top node, the old top node, right? And this is an easy thing to forget in the C language. Right? It's very easy to forget that you needed to deallocate some memory that you previously allocated. Right? So if you have a program that's very long running and happens to use a stack that's being pushed and popped a lot, eventually that program will run out of memory, right? Because you kept on forgetting to deallocate every node. Okay, so print is useful here because it shows you how to iterate over a sequence of nodes, right? So a stack's a collection of items, but it's not like an array, right, where you can just iterate over the elements of the array. Now it's this chained sequence of nodes, right? So you have to be able to iterate over one of these chained sequences of nodes, right? And there's a, do I have this slide somewhere? Hang on a second here. I do. Okay, so printing a stack requires iterating over a sequence, right? And it turns out that iterating over a sequence of nodes is extremely common when you're implementing one of these linked structures, right? The key to this is that you can write a loop starting at some node. You know when to stop when you hit a node whose next link is null, right? Because that indicates that's the last node in the sequence, right? So starting at the first node of a sequence, you can simply follow each next link to the next node until you reach a null node. And so the general iteration pattern is as follows. Right? You make a pointer to a node, and then you set that to your starting node. Right? As long as that pointer is not null, right? So while n, or while n is not equal to null, right? Or while, yeah, that's fine, right? Or while n is not equal to 0, they all work. Right? You can do something with the pointer n inside the loop. Right? You then need to make n point at the next element in the sequence, right? But that's just n equals n next, right? And away you go. All you have to remember is that when you get to the end of the loop, right? After the loop, don't try to use n for anything here because n is null, right? So if you try to dereference that pointer, you're going to run into all sorts of problems. So a little picture of what's happening is as follows, right? So n, I'm going to start at the top, right? Is n null? The answer is no. So, whoops, sorry, slideshow. Right? Is n null? The answer is no. So do something with n, and then n equals n dot next. Right? So n becomes n dot next, or arrow next, sorry, which is that link there. So that just moves the n to point at the next node. Right? Is it null? No. Do something with n. Right? Then follow the link to go to the next node. Right? Is n null? The answer is no. Right? Do something with n. Then follow the link to get to the next node. Now n's null, so the loop stops running, right? Don't use n for anything here, right? Otherwise, you'll try to dereference a null pointer. All right, so that's, and there's the print function, right? All we're doing is with n is printing the node each time, printing the element each time, right there, right? And so that will print a node. Sorry, that will print the elements of a stack. Okay, so I guess we'll end things there since it's 20 after. I guess in the next class, we'll just wrap up the linked node structure, the linked node implementation, and then we'll look at how to implement a generic data structure in C.